Students, today we are going to study experiment number 5 of power system operation control. The title of the experiment is to study load frequency control using approximate and exact model. For this experiment we will require MATLAB simulating software. Now we will study the theory part of the experiment, for which we will require complete block diagram representation of load frequency control of an isolated power system. Now we will start with mathematical model of speed governor system. The output of speed governor system, that means change in y of s, we will connect to the input of turbine system. Now output of turbine system, that means the change in pt of s, we will connect to the input of generator load system. The output of generator load system, that means change in f of s, we will feed back to the speed changer setting. This way we will complete the complete block diagram representation of load frequency control of an isolated power system. Now we will consider that the speed changer setting has fixed setting. So change in Pc of s is equals to 0, and under this condition the load demand changes. So if we consider that the load demand changes by an amount of change in Pd or unit step input function, then the change in Pd of s is given by change in Pd upon s. This operation is called as free governor operation. So under this case the complete block diagram representation becomes this. Here these three blocks will becomes in series, and this is our input and this is our output. Now for this system we will consider the dynamic response. So dynamic response, it is the change in frequency as a function of the time for a step change in load. So for this dynamic response we have input as change in Pd of s and we have output as change in f of s. So we will try to find out the change in f of t with respect to change in Pd. So the dynamic response, when we find out, is given by change in f of t is equals to minus 0.029 into bracket 1 minus e to the power minus 1.717 t, bracket complete. The approximation for steady state is change in f of t is equals to minus 0.029 hertz. So with respect to when we plot the change in f of t or change in frequency with respect to time, we get the approximated graph like this. This is called as first order approximation, and exact graph, this is called as exact response of the system. So in this case what we have studied is that the frequency of the system is not exactly equal to 50 hertz. It has some error. So this error is given by this much amount. So under dynamic response the error is this much amount. So this response must be at 0 condition, so that the frequency will be, or frequency of the system will be 50 hertz. Now we will perform this experiment in the MATLAB simulating software. For that we will require transfer functions. So transfer functions of speed governor system is 10 upon 0.4 s plus 1. Just note down the transfer functions of speed governor system. Note down the transfer function of turbine system, it is 0.1 upon 0.5 s plus 1, and transfer function of generator load system is 100 upon 20 plus 1. Last, the gain of the system is 1 upon 3. Now we will perform the experiment in the MATLAB simulating software. So we will start with the MATLAB. This is the home screen of the MATLAB. Go into the file menu, new, open model. So in front of you, you will find this is untitled model. you just go into the library browser. So, in library browser number of options are there, you find out what component you required. So, we will require the transfer functions. So, I will just find out the transfer function. So, here you can find the transfer function, just right click and add to untitled one. Here this transfer function will be appear in front of you. Similarly, we will require the scope. In similar way, you just add all the blocks you required. Then we will require sum of elements. Then we will require gain. So, in the math operation only you will find the gain, as gain is from the output to the input. So, we have to rotate this gain. So, just put right click the gain block and rotate it, or you just click Control R 2 times, so that the gain block will get rotated. Then the last is subtract, and last is step. In the source option you will find the step signal. Add this step. So, this step will be our input or demanded power. As we required 3 transfer functions, so just copy paste 2 times, one more times we will just copy paste. Now, connect all these blocks. This will be connected to positive, and step, that means our demanded power must be connected to the negative terminals of the subtract. Then connect to this scope, so that we can observe the response. Gain. Now, in this way we have completed the connections. Put here minus sign. Now, change the transfer functions, as we required to put transfer function of speed governor system as 10 upon 0.4 s plus 1. So, change the transfer function 10 upon, in the numerator you just put 10, 0.4, in the denominator you just put 0.4. So, this is changed to 10 upon 0.4 s. Second is 0.1 upon 0.5 s plus 1, 0.1 upon 0.5 plus s into 1. So, this will get changed to 0.1 upon 0.5 s plus 1, and third is 100 upon 20 s. This is our last 100 upon 20 s. So, likewise you changed all the transfer functions and change the gain to 1 upon r, 1 upon 3. So, this way we have completed all the connections. Now, check the step input. Here I have selected by default step time 1, initial value 0 and final value 1. That means, at step time 1 the input on the system is 1. So, the response will get changed at 1 time. So, we will just run the simulation, start the simulation, check the scope. So, you will find the exact response of the system as we have seen in the theory part of the experiment. So, you have observed here the response is settled at minus 0.029 hertz. Here the value is minus 3, that means near about 0.029 hertz. As we have applied the positive input on the system, if you change the input from negative, that means if you decrease the power demand on the system, what will happen? The frequency will get increased. The graph will have we have not changed, final value must be minus. So, once again change. Here you can observe the positive value, that means positive change in the frequency. At time 1 the change in the frequency you can observe, change in the frequency with respect to time. This time the response is positive, or this response is called as exact response. Now, how to plot the approximate response? So, just copy paste this, put in the transfer function everywhere 1 upon 1, that means it is approximated. Just change the transfer functions to 1 only, 1. All the transfer functions we change to 1. And run the simulation. In this second scope, you will find run the simulation once again. In this second scope, you will find the approximated response of the system. Similar response we can obtain for plus value, as I have shown in the theory part. It is for positive change in the input. So, for positive change in the input, you can observe, you can change the time of the input. So, here I have changed time of the input at 0 only. So, response will be at 0 only. Previously it was at 1, now it is at 0. This way you